All right, today is March 29th. I apologize in advance if I start coughing in the middle of the video. I have some allergies going on. Actually went to the doctor yesterday just to make sure that's what it was. So radicals is the name of our new unit, not Malcolm X, but this guy right here. What is another name that you know for this?
Square root.
A square root. Now, the reason we call them radicals, we're actually, I think, only going to be doing square roots. But there is such thing as not only a square root, which you could write like that, but you can have a cubed root, or a fourth root, or a fifth root. So this, by kind of convention, is a square root if there's not a number there. But you can actually put a little number in here to indicate something other than a square root. Right? And all of these together are called radicals. Today we're going to learn about simplifying radicals. So that's the title of this lecture. But before we get into that, I just want to talk about what this actually means and why we're doing it after exponents. There's a couple of reasons. One reason is a radical or a square root is sort of the opposite of an exponent in a way. Because I know like 2 squared equals 4, right? But then I know the square root of 4 equals 2. So the opposite of squared is the square root, in a way. We know the definition of an exponent, right? Like 2 to the second power is 2 times itself 2 times. What's the definition of a square root? I don't know. Or could you put it in your own words? Like, what would you think?
Is it like what exact 2 square numbers multiply to add up to that number?
Yeah. What number multiplies to equal this number? Yeah, exactly. Right? So a square root of x, right, is saying what number, right, what number here would multiply times itself to equal x. That number is our answer. I guess I shouldn't really put it in equals. So if n times n is x, the square root of x is n. It's like what number times itself equals that? What number times itself equals 4? 2. What number times itself equals 100? What number times itself equals 100? 10. So the square root of 100 is 10. There is another way of defining this. I guess I should leave that up there. Actually, before we get to that. So what would you guess a cubed root would be? Like a third root? Like if I said the cubed root of 8. What are we looking for?
What number multiplies by itself 2 times to get that number?
Exactly. So here we're looking for a number that multiplies times itself 2 times. Can you think of a number that multiplies times itself 3 times equal 8? 2. Right? So 2 would be our answer. And you could think of this sort of as the opposite of this, right? If the cubed root of 8 is 2, we know that 2 cubed equals 8. Right? There's another way of defining these. Which is actually using exponents. square root is technically x to the 1/2 power. Cube root is technically x to the 1/3 power, etc. Move these chairs out of the way. So a normal one is a square root. If there's not a number in here, we consider this to be a square root, right? So these are the same. It's just a convention. It seems like square roots are the most common, so we just kind of use that symbol for the square root. Okay. So that's kind of the definition of a square root. You probably have already seen these and kind of know how to do the square root of numbers. And what we're really going to be looking at today is kind of like, well, what about when you can't actually find a number times itself that equals the square root, right? So the square root of a perfect square is pretty simple, right? The square root of 25 equals what? 5. But what about like the square root of 50? How would we do that? How can we do this? Well, it turns out there's kind of some rules for square roots that allow us to simplify them. Sort of like we could simplify exponents. And the basic rule for square roots is you're allowed to take what's inside a square root and break it up into factors. So for example, I know that 50 is 25 times 2. I mean, it's also 5 times 10, but why do you think I'm choosing 25 times 2 in particular?
Because we know what 25 is.
Because we know the square root of 25, right? So if I can find a number that has a perfect square, here's what I can do. I can say the square root of 50 is the same thing as the square root of 25 times 2. And here's where this square root rule comes in. If I have the square root of something times something, that is the same thing as the square root of the first thing times the square root of the second thing. So square roots kind of break up or distribute over multiplication. The video is really fuzzy for a minute, but I think it's back. So the square root of 50 is the square root of 25 times 2, which is the square root of 25 times the square root of 2. And I know the square root of 25. What's the square root of 25? 5. So the square root of 50 is actually 5 square roots of 2. So if I were to kind of write out what we just did in words, step 1, I have to look for factors of this number, right, of whatever number I have, that include perfect square. So 50 is 25 times 2. Step 2, sort of combining both of these things, right? This was right here. Step 2 was I break up the problem into 2 separate square roots. And then step 3, I simplify. simplify the square root of the perfect. Let's look at another example. Another example would be square root. What can I do with that?
Accurate.
Okay. What are some factors of 32?
16 and 2.
And why are those particularly good factors?
Because 4 times 4 is 6.
Yeah, 16 is a perfect square. Okay?
And then we're going to do the square root of 16 times 2.
Okay.
And then we'll do the square root of 16 times the square root of 2.
Mhm.
And then when we do 4 times the square root of 2.
Yes, you will. Very good. Square root of 16 is 4. So, and you'll see this on the first part of your homework. You're going to practice some of the perfect squares, right? So like, if I were to go through all of them, the square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2, the square root of, what's the next one?
Oh, square root.
9. Do you see what I'm doing?
Yeah.
See the pattern? So if you know all of your perfect squares, you know which, oops, square 36 is not 36. You know which numbers to look for. And I mean, you could keep going forever, right? Square root of 121 is 11. The square root of 144 is 12. But those are kind of the basic ones that you want to look for. The cool thing about this too is that once you get up to some of those higher numbers, you can sometimes break them down into smaller square roots. For example, I could have done this a different way. I could have done this problem as a different square root. A different perfect square. 4 times 8. So then I would have ended up with the square root of 4 times the square root of 8, which is equal to 2 square roots of 8. But then I have to say, oh, 8 also has a perfect square. So 8 is actually 4 times 2. So now I've got 2 times the square root of 2 times, let's put the 4 first, times the square root of 2, which is 2 times 2 times the square root of 2, which is 4 times the square root of 2. So sometimes you might have like multiple steps to actually get to your final answer. If you notice that the number left over here in your square root has a perfect square in it, right? So 2 is pretty simple. We know that doesn't have a perfect square in it. But 8 does. Then I have to keep going. I'm trying to get out all the perfect squares that are possibly in that number. Every single one of them. Sometimes just like making a list of these perfect squares will help you as you solve these problems. Like just writing down, 0 and 1 are kind of obvious. You don't really need those. But like 4, 9, 16, 25, 36, 49, 64, 81, and 100, that's going to help you remember, oh, these are the numbers that I'm looking for. Right? Although I will say, even 10, right? If I have 100, there's going to be a 25 and there's going to be a 4 in there. So you might find those smaller ones and then do extra steps to get your answer. Depends. 81. There's always going to be a 9 in 81. So I might pull out a 3 before I pull out the actual 9. It's totally up to you guys. Sometimes it's easier to look for smaller numbers. Sometimes it's easier to look for bigger numbers. Like if I gave you something like 200, right? It's pretty easy to see that there's a 100 in there, right? On the other hand, if I had like 162, I don't know if you'd see the 81 in there right away. So part of this is just a game of like looking for factors. Like, oh, 200, I might see that as 4 times 50. And 4 is a perfect square. But then the 50 is also 25 times 2. So I'd see the 25. Right? We're just kind of looking for factors, and there's no right way to do that. There's not like one way that works and another way that doesn't work. Any way will work that you break down your factors. Yeah?
For 200, like if we did 4 and 50 and then broke up 50.
Yeah, let's do it.
Wait, but when you write it, would it be 2 times 5?
So I'm gonna write it out like this. Let's do it like this. 4 times 50, right? So we'd have 2 times the square root of 50, right? But then we say, oh wait, 50 has a 25 in it. So we do this, right? 2 times the square root of 25. I'm skipping that intermediate step now, which you can do on your work too if you want to. So then I've got, okay, 2, the square root of 25 is what? 5. So I've got 2 times 5. That's the key.
So it would be
Times 2, and 2 times 5 is 10.
okay, cool.
Yeah, so I'm going to have to combine those. The key to remember here is everything is being multiplied together. Everything that we're doing. All right. Any other questions? That was a great question. What other questions do you guys have? If you're ever bored, there's some really cool patterns in these numbers. When you start to look at the perfect squares, it's really interesting. Like the difference between 0 and 1 is 1, right? 1 and 4 is 3. 4 and 9 is 5. 9 and 16 is 7. So the perfect squares, the difference between them is the odd numbers going up. It's kind of interesting. And there's other patterns you can learn. This is one of those things. Math is, I read this thing over spring break that said math is the science of patterns, which is very different from like how we teach math here, right? We're teaching like algebra 1 is this and this and this and this. We don't spend a ton of time looking for those patterns, but they're there if you look. If you're paying attention, there are patterns everywhere in math.
Why are there patterns?
Why? That's a really good question.
Like what, when we figured out
Yeah,
how to do math,
right.
do you think we realized that there were patterns in it?
I think that has to do it with it. It's like when we figured out how to do math, I think the thing about math, it's different from like, figuring out how to make a cake.
Yeah.
Right? Like there's something about math that like actually describes the universe. And so the patterns are there because math is sort of this language of the universe. It's not just something we like made up and said, oh, 1 + 1 is 2. Right? It's actually like based on something that's real in the universe. So there are patterns in the universe. But I don't know, I mean, I would say the reason for each pattern is probably different. And that's what's really interesting about patterns is when you start to ask, okay, wait, why are these patterns here? And if you can figure out why, that's a lot of times, how you would prove a new mathematical idea or concept. Or reprove one that someone else already showed. Yeah.
This is weird, but is it possible for the patterns to like ever change?
That's an interesting question. Like within within a certain pattern, could it change? There are definitely, I mean, in like the history of mathematics, there have been patterns that people thought they figured out, and then they were surprised to learn that the pattern wasn't what it actually looked like. Right? And I wish I could think of an example off the top of my head. But, I mean, I guess here's one. It's like, I don't know if this is totally gonna make sense. But I mean, we kind of looked at this the other day, like x, you know, when we looked at like x to the 5th being like x times x times x, right? And then x to the 4th. Like this is sort of a pattern in a way. But when we get down to x to the 0, that pattern kind of changes. It's like, wait, but x to the 0 is just 1. Huh. So that was like a time probably where you realize, oh.
How did they figure out that x to the 0 was 1?
I don't know how it was originally kind of discovered or whatever. I mean, we figured it out by thinking about something like this, right? X to the 4th over x to the 4th would be x to the 4 minus 4, which is x to the 0. But we know that anything over itself is going to be 1, right?
Yeah.
I don't know if that's how it was originally kind of discovered, but yeah, I don't know. It'd be. I'm gonna try to see if I can find the answer to that question. I'm gonna look up and see, like, you know, patterns that surprised mathematicians. I'm gonna turn this video.